All right. This is a bonus video, extra video on processing globular cluster images. Now, normally you can follow the regular instructions, the same instructions you use to process the open cluster images, and everything's fine. But sometimes with the globs, you can encounter some problems. And it's because there are just so many stars in here, a lot of stars, and they're very concentrated, about a single point in the image. And this can lead to some problems sometimes. You can have problems with photometric calibration, and you can have problems with alignment. So let's talk about photometric calibration first. So here I've processed all my data per the normal instructions, created a group, colored the BVR images, turned off the I image. Let's see that here. And if we come over here to display settings, I've linked the layer's pixel value. I've gone into photometric calibration. And you're at the point where you're going to measure your 0 points, right? We're using the stars to set the relative levels of the red, green, and blue. Here's the red, here's the green, here's the blue. And we want to measure these 0 points. So you press the button, you scroll down, there's a status bar, and it works its way up to 100%. And when it's done, it updates the 0 point numbers, and you can press the calibrate colors button, and you're good. Now, sometimes you can get stuck here. Gets up to 100%, and just spins and doesn't stop ever. And that's because it's failed. It's failed on one or more of the layers. It was not able to measure a 0 point. And it failed because there are just too many stars in there. So if you find yourself in that situation that this task won't complete, or it completes and it gives you an error message saying it wasn't able to do it for one of the layers, then what you do is cancel out of this, come up here to settings, go to photometry, slide on down to the last group here, source extraction settings. So the problem is there are too many stars. It's getting confused. So we want to extract fewer stars, just the bright ones. And that's controlled by this first box called threshold. It's currently set to 2.5. So it's going to take any blob of light that's 2.5 times the noise level or greater. And it's giving me too many stars. So try changing it to 25. And it will only take stars that are 25 times the noise level or greater. So change it to 25, come back here, photometric calibration, try again. Press the button, see if it completes. Should run faster. If fewer stars you include, the faster it runs. A little bit less accurate because we're throwing away information, but at least it will complete. If it doesn't, come back to settings, photometry, slide on down and up it again, maybe 100. When you're done, if you want to put it back to the default settings, press the button, 2.5. Okay. Now this one didn't have photometric calibration problems, so 2.5 is fine. And I calibrated it, and I look at this and it doesn't look right. So we're now transitioning into the next set of problems, the alignment problems. I look at it and it looks kind of greenish in the middle. Something's not right. We zoom in, look at these stars. Something's really wrong here. We have little tears in the image where the red layer is coming through, but the green and the blue aren't. Something's not right. Okay, so this has to do with alignment. Let's go back to one of the individual images here. zoom to fit. When Skynet takes an image, it puts a WCS on it. It tries to. If there aren't enough background stars, it fails. Like with planets, we didn't have WCSs for almost all of our planet images. But with these deeper images, you should almost always get a WCS, unless you're looking through a lot of clouds or something. So what Skynet's doing is it's extracting stars from the image and the positions, comparing it to catalogs and catalog positions, and using all this information to come up with a conversion from a pixel location in your image to right ascension declination. Down here at the bottom, it says the RA in the deck. Now, if you move your cursor around and there are numbers there, your image has a WCS. But doesn't mean it's a good WCS. Now, most of the time it's fine. And most of the time you have stars spread relatively uniformly across your image, and Skynet's fine. The WCSs are accurate. But when you have a lot of stars and they're very concentrated, you can have problems with the WCS. Two types of problems, if you want to get into it. First of all, if we zoom into the center here, maybe I'll change to bright target so we can see the stars. Or I'll back out a little bit here so we can see them. A lot of stars in there. Stars on top of stars on top of stars. And we may get some misidentifications. We extract a star, we try to find it in the catalog and grab its position to build the WCS. But since there's so many stars, we can have confusion problems and we get the wrong star out of the catalog, the wrong position. If we do that enough times, well, garbage in, garbage out. We're building the WCS from the star positions. And if we're grabbing the wrong stars out of the catalog, because it's such a mess in here, then we'll end up with the WCS with errors. That's one issue. It's just too crowded. The second issue is even if we were doing that right, no misidentifications, almost all the stars are in this tiny little patch. So when the WCS solution solves, you get the plate solve, it focuses all of its power right here. And so if there are no misidentifications, they'll get that part really accurate. But by the time you get out here in the outskirts, the errors build up, and there are very few stars out here compared to the center. So you can have errors that increase radially, and if there are mismatches, you can have errors in the inside too. So let me just show that. I'll go back to default here, zoom to fit, and I'm going to shift arrow through these images. May be hard to see at this scale, but the stars are bouncing around. Here, I'll zoom in, shift arrow back through them. See how much the stars are moving? Stars are moving by more than a star. Now, when you first load your images into Afterglow, if you scroll through them like this, often you will see stuff move around because with each exposure, the telescope is repointing and the pointing's not perfect, so we expect stars to bounce around a little bit. But if I go over here to settings, you can see I've already turned on sync orientations. And sky mode means it's using the WCS to align them in the viewer port. So as I scroll through, they should all be aligned in the viewer port with the WCS. The stars should be stationary. And the fact that they're not, that they're bouncing around, is telling us that the WCSs are indeed erroneous by that amount, by more than a star. And this leads to problems when you process your image. If we come over here, you start with the cosmetic cleaning, that's fine. Then we go down to the aligner, and here we are in WCS mode. With our deep sky images, we use the WCS mode to align. We use the coordinate system on each image to align. But if the coordinate system is erroneous, then the alignments will be poor. And then when you go to the stacker, here I am in the stacker. Let me go back to the file list. I'll filter on B, for example. And I have everything set here. We have Chauvenet rejection turned on with the low and high turned on. Histogram scaling, smart stacking is turned on, propagate mask. We have all the standard settings here. And we're going to stack these 5 images using these settings. But the images are not aligned well. So the first set of problems that you have when they're not aligned well has to do with the Chauvenet rejection. Now remember, the reason we have Chauvenet rejection in there is it gets rid of outlying pixels. You know, suppose something made it through the cosmetic cleaner. Maybe we had a cosmic ray hit a little cluster of pixels, and so the cosmetic cleaner didn't remove it. But it's just in one image. It's not in the other 4. What Chauvenet rejection does is at each pixel location, it looks at all 5 images here, and it says, oh, these 4 are very much the same, but this one's very different. And it says, we're not going to use that pixel. We're going to get rid of that pixel, and then it moves on and checks the next pixel, the next. It works great if everything's aligned. If it's not aligned, then in some images you have a star there, and other images you don't. And so sometimes it'll try to get rid of the star, or part of the star, side of the star. And that's what we're seeing. Let's go back. Let's get rid of the filter. Here we have the color combined image. That's what we're seeing. These tears, they're primarily in the green. Here we go. See right here? This is a region that got Chauvenet rejected, and here and here and here. It's because of the misalignments. Sometimes it doesn't know if it's a star or if it's an outlier, because in the other images, there's no star there because it's misaligned. And so you have some parts that get clipped out in some of the filters, and then other filters bleed through. And so you get this mess. And the human eye will then see this as very different colors than it should. It looks kind of greenish or bluish green here in the middle and almost orangish in the outskirts. Something's not right. When you zoom in, you can see what's not right. Okay, well, what can you do about it? Kind of the Band-Aid fix, and I recommend you try this first, is just turn Chauvenet rejection off. If you turn it off, then it's not going to do this. You know, if you do have some stray, like a cosmic ray hit, it's not going to get rid of it. But at least it's not going to do this to each and every star. So what do we get? We've turned off Chauvenet rejection. So instead of this, we now get this. And that's a lot better. We're no longer tearing the sides out of all the stars. So that's certainly better. We zoom out, the colors are closer to natural. Still not perfect, but closer. Here's what it looked like before with the weird blue-green. Okay, that's better. But we didn't really correct the underlying problem. We turned off Chauvenet rejection, which was tearing the sides off of stars, but it was tearing the sides off of stars because the underlying images were misaligned. By turning off Chauvenet rejection, we didn't fix the misalignment. They're still misaligned. And you can really see that if you come into the outskirts here. You see the color separation? Since the images are misaligned, when we stack them, one, they get kind of blurred and stretched out, but they're blurred and stretched out differently from filter to filter. Here you can see the green is a little bit more on the left, and the red's a little bit more in the lower right. We go to a different part of the image, and the color separation will be different. Now, if we zoom out, you can't see the separation, the color separation of the stars, but it does affect the color that our brain interprets. when they're separated like that. Still, this is perfectly fine to turn in. You can turn this in. The Band-Aid usually is more than sufficient if you're even having a problem with the glob. Most globs process just by the usual instructions. Now, for the rest of this video, I'm going to show you how to get the alignment good, how to fix the underlying problem if you want to. It's a bit of work, but it does make a difference. And let me show you the difference to start out. So here, this is the misaligned version. And once we do the alignment correctly, we get this. Before, after. So first of all, if everything's properly aligned, the stars will be tighter and you won't get the color separation. If we go to the outskirts now, you don't see color separation. It's a whiter, bluer star. This star is a little bit redder than that star. You know, all the underlying images are properly aligned, so we get nice, clean stars, and each has its own unique color. And the human brain sees it differently. When you zoom out, everything was kind of yellowish before. Now we're getting true colors. Some stars are white, some stars are a little bit redder, etc. Okay. So, how did I do that? Well, let's process these images, or at least start to. The way we do it is we do the alignment like we did with the planets. It's a manual alignment. Now, with the planets, we only needed one star. Remember, we find a reference point, we used the planet, and we clicked on it manually in each image. But we only needed the one there because all those planetary images were taken back to back to back. These images are taken at different times, sometimes different days. Telescope's in a completely different configuration, gravity's tugging on it different, and that can rotate the field. So instead of one star, you would need two stars, except in this case, some of the data was taken with a different telescope. Some of the data was taken with Prompt 6 and some was taken with Prompt Meckering, and they have different scales. So in addition to rotation, we have scale, so we need 3 manual reference stars. And you want to pick them kind of spread across the image. Okay, so I'm going to go back to the original data here. And you want to find your smallest field. If you're mixing data from different telescopes, this is Prompt 6, here's Prompt Meckering. Okay, so I want 3 stars well separated on this image here. Let's start with this one here. It's a nice bright one. It's off in the corner. And so I'm going to go to Source Catalog, include from other files. Nothing's there. If something was there, I'd empty it out. No planet centroiding this time because this is just a star. And let's go back to the first image and we'll click. I'm going to turn off the include so those don't distract me with my clicking. And you're going to want to pay attention. Make sure it lands in the middle. If it lands not in the middle, just click on it again, delete it, and then try again. We have 20 of these. There is a big jump. And another big jump. That's the last one. Then we include from all. And I'm going to, in this case, select them all. merge them. It's going to be labeled 0. Okay, that's 1 star. Now I need to find another star. Let me go back to that Meckering image and something someplace else. Let's maybe use the star right here. Go to the first image. Turn off. Include. Same deal again. Okay. Include them all. Now this time you can't select all. You have to, because you don't want to select the ones you already selected. So you have to select them by hand, 20 clicks. Merge these. They're going to be called 20. Okay. Now we need a third. And I'm going to go back to the small field, pick something in a different part of the image. Let's use this one. Go to the first. Turn off include. Play the most boring video game ever. Okay. Turn them all on. The zeros, the 20s. Okay. Click on these 20. By merging, we're just telling Afterglow these are all the same source. It's called 40. Okay. So we have our 3 stars here, here, and here. We're going to go to the aligner and we're going to do sources manual. Select everything, select the reference image, crop. We don't need skew, but we do need rotation and scale. Sources manual, and then we select 0, 20, 40. Okay. Don't worry about these warnings here. Let's see how the alignment did. Yeah, just load these in real quick. All right, tell it's much better. Okay, so if I flip through them, you see there's no motion of the stars. They're all staying put. I can zoom in. As I slide through them, they're all staying put. It's all nice and good. And so then you proceed to the stacker. You can turn Chauvenet rejection back on because things are aligned and stack in your different filters, group and color, and you'll end up with download it and you're good to go. Okay, that's it.